The picture.
So let's get started by taking roll first, as usual. Today is 19th.
My boyfriend, right? What do they do? They do every Sunday. Looks like I'm texting you every Sunday. Yes. I hate discussion posts. I just, like, there's nothing I hate more than discussion posts.
Okay, answer to your names, please. Hersey,
Yeah.
Rani, Gilcrease, Lucky.
Here.
Luna.
Here.
Oh, Lucky's here. And Luna is here as well. Macias, McKinnon is here. Morris is here. Powers is here. Renfro, Salvador, and Spivey is here. Okay. So we're going to continue from where we left off the last time. And the very last thing that we discussed was how do we determine the pH of a solution of of a strong acid and a strong base, right? And just to briefly recap very quickly, using this example, these two examples that we worked on. Basically, it comes down to the fact that in the case of strong acids and strong bases, they both undergo 100% dissociation, right? So if you look at the stoichiometry, or if you write down the equation for the dissociation of a strong acid or a strong base, then based on that equation and based on the initial molarity of the acid, you can determine the molarity of the hydrogen ions in the case of acid directly, and then you can calculate the pH. Or in the case of bases, you can calculate the concentration or the molarity of the hydroxide ion, and then find the pOH and then find the pH, right? So these two examples that we did the last time basically is basically what we did when it comes to determining the pH of a strong acid or a strong base. Now, what we're going to see in today's class is that when it comes to weak acids and weak bases, things are a bit more complicated. Because for one, unlike strong acids and strong bases, you cannot assume 100% dissociation, right? So we're going to see how that affects how we approach solving problems where we need to determine the pH of such solutions. So the first thing we need to talk about is what are called, in some textbooks they call it acid ionization constants. In other textbooks, they call it dissociation constant, which is what I prefer to use personally, right? And these constants are always in association with weak acids. So as we said before, a weak acid will undergo partial dissociation, right? And just to remind you what that means, it means basically that only a small fraction of the acid molecules will be converted to ions, right? So as a result, you're going to have this back and forth, right, between the hydronium ion and the conjugate base of the acid and the acid over here, right? So because it's a system in equilibrium, we can write down an equilibrium expression for this, right? This is another way of expressing the same thing. So if we're using this equation here, then the equilibrium equation for this would be, as we learned in the previous chapter, the product of the concentration of the products divided by the product of the concentration of the reactants. There's only one reactant here, so that term is down here, all right? And this is equal to a new equilibrium constant, and we call this the acid dissociation constant, or the acid ionization constant, all right? And it's very much an equilibrium constant, just like Kc, just like Kp. The only difference is it's applied to a system like this, where we're dealing with a weak acid undergoing partial dissociation to form the hydrogen ions and the corresponding conjugate base, all right? As such, the only factor that will affect Ka, the dissociation constant, is temperature, all right? And that's the reason why, if you look at information in chemical literature about dissociation constants, it is typically quoted at a particular temperature, usually 25 degrees Celsius, all right? So one of the utilities of the Ka value is that we can use it to make comparisons between weak acids to say which one is stronger, right? And of course, the stronger the acid is, the higher would be the concentration of the products, right? And the lower would be the concentration of the reactants, everything else being the same. So basically, we can conclude, if we want to make comparisons between two acids, basically we can conclude that the higher the Ka value, the greater the strength of the acid. So if you have two acids that are weak and you have their Ka values, all you have to do is compare the Ka values. The one with the higher Ka value would be the stronger of the two weak acids, all right? So that's one of the usefulness of the dissociation constant. So what you're looking at here is a list of different weak acids and their dissociation constants. And you'll see that at the top of this list is hydrofluoric acid. Hydrofluoric acid is one of the stronger weak acids that exist, and its value is given here, which is, as you can see, it's a small value, 7.1 times 10 to the minus 4. And therefore, what you'll find is that there are other weak acids that are weaker than hydrofluoric acids. So for example, if I could jump down here to hydrocyanic acid, its Ka value is 4.9 times 10 to the minus 10. So this is significantly weaker compared to the hydrofluoric acid. Now, this list is not by any means comprehensive because I need to show you, which I've posted in Canvas. Okay. Okay, so let me go to files. And then tables. And then dissociation constant. So this will be made available for you for your, your next test, right? So this is a more comprehensive list of different weak acids and their Ka values. Now, there are some acids that can lose 2 or more hydrogen ions, right? So basically what you find is that you can have more than 1 Ka values, right? So for the first dissociation, it's called Ka1, right? And then if you have another hydrogen to be lost, then for that second dissociation, that would be Ka2, right? And then you can have Ka3. I've never seen a Ka4 value for any weak acid. So basically, that's as far as you're going to go as far as that is concerned. So for example, if you look at arsenic acid, right? This is the formula. You'll notice that there are 3 hydrogens here, right? So therefore, for the first one, for the dissociation for the first one, that's 5.8 times 10 to the minus 3. And then for the second one, it's 1.1 times 10 to the minus 7. And for the third one, it's 3.2 times 10 to the minus 12. And this is the pattern that you'll see in the case of such acids, in that the first dissociation is usually the strongest, right? So the Ka1 would be the highest value, and then Ka2, and then Ka3, all right? And the reason for that is very simple. If you think about it, let's use the example of arsenic acid to demonstrate this. So this has 3 hydrogen atoms, right? So it will take a certain amount of energy to remove the first hydrogen ion, right? The result of that loss would be, let me write down the formula here. So in the case of, okay, oh, it's not plugged in. Okay, so in the case of H3ASO4, the first dissociation would be H plus H2ASO4 minus, right? Now for the second dissociation, in order for you to have this occurring, you need to remove a hydrogen ion which is positively charged from an ion which is negatively charged to form HASO4 2 minus, right? So that is more difficult, right? To remove something positive from a structure which is already negatively charged, that takes more energy, right? So as a result, the Ka2 value for this would be less than the Ka1 value for the first dissociation. And then when you get to the third dissociation, O4 2 minus, in order to remove the next hydrogen ion, you need more energy because now you're removing a hydrogen ion which is positively charged from something that has a -2 charge. And the resulting structure would be AsO4 3 minus, right? And the Ka value for this would be greater than the Ka2, which would be greater than the Ka1. And this is what you'll see as a pattern emerging when you compare the Ka values for the different dissociations from the same acid. If the acid has more than one hydrogen atom or more than one hydrogen ion to lose, right? So that's basically a pattern that you'll observe when it comes to the Ka values. All right, let me clear this here. And let me go back to PowerPoint. Okay, so that's that as far as, oh, by the way, this side here, we're going to talk about Kb values, right? That's for bases, but that's for later on. And you're going to see the relationship between the Kb for a conjugate base and the Ka for the respective acid. But before we do that, let me, hold on, this is going back. Okay, let me also define another term which will become important in future calculations. Percent ionization, also in some textbooks they call it percent dissociation, right? It's another way of measuring, it's kind of related to Ka, another way of measuring the acidity of an acid, but it's based on the concentration. The percent ionization is equal to, oops, hold on. It says here the ionized acid concentration at equilibrium divided by the initial concentration of acid. I think a more accurate way of expressing it is percent dissociation is equal to, oh, I think I have it down here actually. Okay, here it is. I was about to repeat myself. Percent ionization or percent dissociation would be equal to the concentration of the hydrogen ion, and I should add here at equilibrium, so then put EQ here, which indicates that the concentration of the H plus is measured at equilibrium, divided by the initial concentration of HA, the weak acid, times 100%, right? So that is also used as a measure of the strength of the acid, but it's not 100% accurate because it involves a concentration and the concentration can change. The Ka value is a more accurate way of determining or comparing the strengths of weak acids, all right? But we're going to use this actually later on when we do the calculation of pH of weak acids, all right? And there's a graph below, which basically is a plot of ionization energy versus the initial concentration of the acid. And this demonstrates the fact that for weak acid, the percent ionization varies with the initial concentration of the acid, all right? So basically, the greater the strength of the weak acid, the lower would be the percent ionization of that acid. And when you compare that to a strong acid, well, a strong acid dissociates 100% anyway, right? So therefore, regardless of what the concentration of the acid is, the percent dissociation will be 100% as far as strong acids are concerned. But as far as weak acids are concerned, as you increase the concentration, the initial concentration of the acid, the percent ionization drops. And as you can see, it drops very severely initially, and then it kind of levels off, but not 100% constant. All right? So that's percent ionization of acid or percent dissociation of an acid. All right? Okay, so let's look at a problem where we're asked to find or calculate the pH of a weak acid. So this weak acid is hydrofluoric acid, and the molarity is 0.5 m at 25 degrees. Oh, by the way, this table here that I showed you earlier, let me go back to it. Just a brief thing I forgot to mention. You'll notice it says at 25 degrees. That's a standard that is accepted pretty much universally, right? Whenever you see Ka values being quoted for a particular weak acid, you can assume it's at 25 degrees, unless stated otherwise. All right, so going back to this here, question is asking, what is the pH of 0.5 m hydrofluoric acid solution at 25 degrees Celsius, right? So this would be the equilibrium system. It's not 100% dissociation because it's a weak acid, right? So we need to determine what the Ka is. All you have to do is look it up in the table. And if you do that, you're going to see that the Ka is equal to what is stated here, which is 7.1 times 10 to the minus 4. Let me get rid of this here. Okay, so that's a Ka value for hydrofluoric acid. And this is the equation relating the Ka to the concentrations of the different items, right? So you're going to need that in order to answer this question, all right? So in order for us to answer this question, since we know that the reaction or the dissociation will not go to 100%, what you have to do is set up an ice table, right? Where you record the initial change and the final equilibrium concentrations of the different components in this system, right? So assuming that initially you only had HF, then that concentration would be 0.5. Well, they had a 0 here, but that's what was given initially. And initially, before any equilibrium occurs, the concentrations of the H plus and the F minus would be 0 as well, all right? Now, we don't know what the change is, right? In fact, we need to find the change. So we don't know what the change is. So what we're going to do is assume that the change in the concentration of HF is minus X, right? We don't know what it is, so we're just going to use an unknown term for that, minus X. Now, if the change in the concentration of HF is minus X, based on the stoichiometry of the equation, that means that the change in the concentration of H plus would be plus X, and the change in the concentration of F minus would be plus X as well, right? So to get the equilibrium concentrations, all we have to do is add the values in this line to the values in this line, right? So what are we going to end up with? We're going to end up with 0.50 minus X here, as far as the concentration of HF is concerned. We're going to end up with the concentration of H plus and F minus being X and X in each case, right? So these are the equilibrium. Yes, sir.
So in the part, how do you know if it's plus X or minus X?
Because you're starting off with the acid first and nothing on the other side. So that means that the reaction must shift to the product side in order for equilibrium to be achieved, all right? Okay, so now that we have these terms representing the concentration at equilibrium for the different substances, then we can plug each of these terms into this equation here, right? So when we do that, we're going to end up with this here, because X is the concentration of H plus, X is the concentration of F minus, so X times X will give you X squared. And then down here, you're going to have the 0.50 minus X, and you're going to set that to be equal to 7.1 times 10 to the minus 4. Now from here, it's all algebra, right? Because basically you're asked to solve for X. However, we can make life easier if we make an assumption. But let me just say that if you make this assumption, then you have to see whether or not the assumption that you have made is valid. And we're going to get into that shortly. So the assumption that we're going to make here is that because the hydrofluoric acid is a weak acid, that means that X is very, very small. So small that when compared to 0.50, 0.50 minus X would be approximately equal to 0.50, right? So basically what we're saying is that we're assuming that X is equal to 0, right? Or a number so small that it's effectively 0, right? So that simplifies this equation here to this, all right? So instead of 0.50 minus X, we simply have 0.50 here, and then we solve for X, which is relatively easy. X squared is equal to this times this, which gives you this, and then you find the square root, and you're going to get X equal to 0.019 m, all right? And that would be the concentration of H plus. Based on that, you can calculate the pH, because remember now pH is minus log the concentration of H plus, which would be equal to minus log of 0.019, which would be equal to 1.72, all right? So that would be the pH that is calculated based on the assumption that X is so small compared to 0.50 that we can ignore it, right? However, that's not enough for us to make that assumption. We have to test to make sure that the assumption is valid. How do we do that? By calculating the percent dissociation of the acid. And there's a criteria that is used in most textbooks, and that is if the percent dissociation is less than 5%, then basically the assumption would be valid and therefore the results of that can be accepted, right? So let's calculate the percent dissociation in this case. Now, in this case, the concentration of the hydronium ion is 0.019, and the concentration of the acid initially was 0.50. So basically, we divided 0.019 by the 0.50 times 100%, and we get an answer of 3.8%, which is obviously less than 5%. And because it's less than 5%, then basically the approximation is okay, and therefore the calculated pH would be acceptable. All right? Now, the thing is, if you determine the percent ionization or dissociation to be 5% or greater, then we cannot make that assumption that we made earlier. And therefore, it's a more complex thing where you'd have to actually derive, based on the initial setup, a quadratic equation and then solve for x. You're going to get two terms for x. We're going to do an example of that type shortly, all right? But for now, we're talking about a situation where the assumption is valid, where the percent dissociation is less than 5%, and therefore we can basically accept the pH value calculated based on that assumption, all right? Okay, any questions about this? Any questions? Any questions? Okay, I think I have an example here. Actually, yes. In this example, the pH you're asked to calculate is for same acid solution, but more dilute, 0.05 m, right? So it's the same setup as before, right? If we make the assumption that we made before, that x is small, then we're going to end up with this expression right here, just like we did earlier. And then when we solve for x, we get 0.006. But guess what? When you divide the when you divide the 0.006 by the initial concentration, you're going to get 12% as the percent dissociation. 12% is obviously greater than 5%. So therefore, the approximation that we would have made based on that fact is not okay. And what that means is you'd have to go back to the original setup where you had x squared over 0.05 minus x equals to 7.1 times 10 to the minus 4. So you have to go back to this right here and solve for x the long way. You have to do some cross multiplication and distribution and all that good stuff from your algebra class. And you're going to end up with a quadratic equation, and then you're going to solve for x. And x will give you the concentration of H plus, and then you can find the pH. All right? I won't do that for this example. You may try this at home. But there's another example that I think I have coming up, which deals with that situation. But before we get to that, let's talk about the steps involved in solving weak acid ionization problems. Usually this involves calculating the pH of such acid solutions. First, you have to identify the major species that can affect the pH. In most cases, you can ignore the auto-ionization of water because water does contribute some hydrogen ions, but relatively small. So for the vast majority of cases, you can ignore the contribution of hydronium ions from water, and you can also ignore the concentration of OH minus because you can determine the concentration of OH minus based on the concentration of H plus. If you recall, we said that the product of the concentration of OH minus and H plus is a constant. So if you know one, you can easily determine the other one. It's very important that you use ICE tables to determine, the setup so that you can basically determine what X is ultimately. And then you write the Ka value or the Ka term in terms of equilibrium concentrations, and then you solve for X by the approximation value or method, I should say. In other words, assume that the amount of X is small compared to the initial amount of acid, and then if it is valid, then you can go ahead and calculate your pH based on that. If not, then you have to solve for X exactly, which will involve a quadratic equation. And then you can calculate the concentrations of all species and or the pH of the solution based on whatever the question is asking for. Okay, so these are just basically the steps. You don't need to memorize these because what you'll find is that when you go through problem solving, you're basically will go through the steps automatically without even thinking about it too much. Okay, so here's an example now where I think the approximation that we would use would not be valid. So in this case, they gave you the concentration of a monoprotic acid, so they're not specifying what the acid is, and they gave you the Ka value for that acid, right? So this is the equilibrium hypothetical reaction, showing you how the acid dissociates. And the Ka value, they gave you is 5.7 times 10 to the minus 4. So based on this, you're going to set up your ice table, initial change and equilibrium. So initially, you're going to have 0.122 m of the acid. You're going to have no H plus and no A minus. And then the change, we're going to say, is minus X for the HA plus X for the H plus X for the A minus. So at equilibrium, you're going to have 0.122 minus X for the HA. You're going to have X here and X here for the H plus and A minus respectively. Then you're going to plug these into the Ka expression, and this is what you're going to get. And then you're going to make your approximation that X is small compared to 1.22, such that, 1.22 minus X is equal to 0.122. And then that simplifies this equation to this, and then you solve for X. And then you end up with X being equal to 0.0083 m. Then you have to find the percent association because you want to see if the approximation is valid. And what do we find here? When you divide the concentration of H plus by the initial concentration of HA, we end up with 6.8%, which means that the assumption that we made here would not be valid, right? So what that means is that we have to go back to this equation right here. And we have to solve it the longer way. So, okay, so the approximation is not valid. So we have to go back to this equation here. So, of course, you should be familiar with the type of algebraic manipulations that you need to perform. So ultimately, you're going to get to your quadratic equation of this form, right? And that's the reason why I said to you guys, make sure that, especially during test time, that you have those fancy calculators, what is it, TIA, whatever, that you can program, right? You can put the A, B, and C values, and then press execute, and it will give you the possible X values, and then you can work based on that. So you can use that to solve a problem of this type, all right? In this particular case, or you can go the longer road, but I'm quite sure that would be a bit of a headache during test time especially, so it's up to you, all right? But if you solve this particular equation, you're going to get two values of X. Only one of them would be valid, right? Can you guess which one would be the only valid one? The positive one, right, exactly, right? So for the purposes of solving this problem, you can ignore this one right here. You're going to use this here, which represents the concentration of H plus. And the question is asking for the pH. So basically, concentration of H plus will be equal to that value of X. And therefore, to find the pH, we just simply do minus log of that value. And you're going to end up with your answer being 2.09 in this case. And that's basically how you solve this problem, all right? So as you can see, it is not as straightforward as calculating the pH of a strong acid, right? In the case of calculating the pH of a strong acid, we assume 100% dissociation, and therefore we can, based on the equation itself, without doing any fancy calculation, we can determine the concentration of the H plus, and then from there, the pH. In the case of weak acids, as you can see, there are several steps that you have to undergo, all right? Okay, any questions about this? Any questions? Any questions? Let me see. Any questions out there in Zoom? Going once?
Nope.
Okay. Let me check the assignment. So let me bring up assignments 4. Okay, so let's see. Oh, by the way, have you guys tried? I told you guys to try what questions again? I think we did 4, right? And 5. Did we do 6?
We didn't get to 5 in the last policy.
Oh, okay.
Six and seven.
We did 6 and 7? Oh, okay, I'll take your word for it.
Is it, it's just 2-6 and 2-7 in the assignment.
Oh, right, yeah, my numbering system, I screwed up on that. My apologies. So you're talking about this one here? We haven't done this one, right? Okay, this one is rather simple because they gave you an acid solution with a pH of 4, and then you diluted 10 mils to a final volume of 1,000 mils. So the question is, what is the pH of the resulting solution? Now, what equation comes to mind when you see this word? Does this look familiar? The dilution equation? All right. So basically what they're asking for is the pH of the resulting solution, right? So what I would do is rearrange this to find C2, which is equal to C1 V1 over V2. So what is C1? Well, C1 would be the initial concentration, which is equivalent to the pH of 4. Now, the relationship between the pH and concentration, one way of expressing it is the concentration of H plus is equal to 10 to the minus pH, right? In this case here, it would be 10 to the minus 4, right? M multiplied by V1, which is 10 mils, divided by V2, which is 1,000 mils. So what does this work out to give you? That gives you 10 to the minus 3 divided by 10 to the 3, so that would be 10 to the minus 6. M, right? So that would be equal to the concentration of H plus for the more dilute solution. So therefore, the pH of the solution will be equal to what? Exactly. Minus log of 10 to the minus 6, which would be equal to 6. And that's it. All right? Any questions? Any questions? Any questions? No questions? Can I clear this? Going once, going twice. All right. Let's see what's next. Okay, yeah, these are relatively easy. Let me see here. I don't want to go through all of them. All right, tell you what, I'm going to do the first two for number 7, all right? So in the case of 7A, the question is asking for you to determine the pH of the following solution. Whenever a question is asking you to determine the pH of an acid solution or a base solution, the first thing you have to ask yourself is this a strong acid or is it a weak acid, right? And if you recall, I don't want to embarrass you guys by asking you again, but there are 6 acids that you need to memorize as weak acids. Or should I embarrass you? What are the 6 acids? Not weak acids, I'm sorry, strong acids. 6 acids that are strong acids. Sulfuric acid, hydrochloric acid, hydrobromic acid.
Sulfuric.
I think we mentioned that before, right? Yeah. Sulfuric, let me write this down. I'm forgetting. Sulfuric, what was the other one that was mentioned? Hydrochloric? Huh? Hydrobromic, okay. So far, so good. 3 more. Perchloric. 2 more. Nitric, 1 more.
Same, but is it HI?
Hydroiodic, exactly. Okay, please, folks, remember these acids as your strong acids. pretty much all other acids that you'll be given will be weak acids, unless you're told otherwise, all right? But when you see these, make sure you identify them as strong acid. So hydrobromic acid is one of them, right? So since we know that this is a strong acid, what does that mean? That means that this undergoes complete dissociation, right? To form H plus and Br minus. So basically, whatever the molarity of this is, the molarity of the H plus will be the same, which means that pH is equal to minus log of 4.5 times 10 to the minus 3, right? Get my calculator. Okay, so 4.5 times 10 to the minus 3 log, and then minus, so I got, and please correct me if I'm wrong, but I got 2.35. All right? And that's the answer for that one. Okay? Again, when it comes to bases, same thing. Now, bases are easier to memorize because remember I said that the strong bases are hydroxides of groups 1 and 2, right? So potassium hydroxide is potassium is in group 1, right? So therefore we know that this is a strong base. So what this means is that potassium hydroxide will undergo complete dissociation to form K plus and OH minus. So again, the concentration of OH minus in this case is going to be equal to whatever this is, 3.67 times 10 to the minus 5. Now, my question to you is, that's the concentration of OH minus. How will you use that to determine the pH of the solution? Yes, sir.
14 minus the OH.
Okay. Okay, you're right, but I want to explain the reason why what you're saying is true. Remember the relationship. pH plus POH is equal to what? 14.00, right? So you need to remember this. I don't remember if this is in the tables. Let me check something here quickly. That equation may be in the tables. Let me go here, close that. Tables. Let me see. I know some of the tables contain some equations. I don't remember if that is one of them. If not, you have to simply remember that equation. Scroll down.
I see it.
Well, they gave you Kw is equal to concentration of OH minus times H plus.
I see it, it's
Where is it?
14. It's under the pH equals -.
Oh, okay, yeah, it's there. Okay, so that would be available for you guys. All right? Okay, so let me go back to this now. Okay, so as he correctly said, first what you have to do is find the POH. POH is equal to minus log of 3.67 times 10 to the minus 5. Let me see what I get. So 3.67, oops, something is wrong here. 3.67 times 10 to the minus 5. And then you find the minus log of that. And because this is 3 sig figs, this would have to be written to 3 decimal places. So that would be 4.35, right? And therefore the pH would be equal to 14.00 minus 4.435. So according to my calculation, this works out to be equal to 9.56. And that's where you get that. All right? Any questions about this one? Any questions? Okay, I'm going to leave the rest of number 7 for you to do. If you have any questions about that, please let me know. I take it it's okay for me to clear this, right? All right, let me clear this. Let me do that, and let me scroll down. So try the others in number 7, and let me know if you have any issues. So, okay, so now we get to number 8. So number 8, it says that the pH of formic acid is what you're trying to find. It gives you the molarity, it gives you the Ka value, right? So we did a couple of examples of this type. So let's go through the steps. The first thing I would do, and typically when I do problems like these, being the lazy person I am, instead of writing out the formula for formic acid, you could look it up. It's in the tables, but you could just use HA to represent formic acid, right? So HA will dissociate to form H plus and A minus. Okay, now, let me start you off a bit. You're going to construct a nice table, right? So what would be the initial concentration of HA that you would put here? 0.065. And the initial concentration of H plus and A minus would be 0 and 0 respectively. And then what do we put in this line down here? Minus X for the HA, plus X for the H plus, and plus X for the A minus, right? So down here, you're going to add, to get the values down here, or the terms down here, you're going to add the first line to the second line. This becomes 0.065 minus X, this becomes X, this becomes X. Okay, so the Ka expression would be equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA. And then we put in the terms. You're going to have X times X at top, as the numerator divided by 0.065 minus X, and that will be equal to the Ka, which is 1.8 times 10 to the minus 4. And what do we do next? We assume that X is much less than 0.065, such that 0.065 minus X is approximately equal to 0.065. So what that means is that this expression now becomes X squared over 0.065 equals to 1.8 times 10 to the minus 4, which means that we can solve for X. That will be equal to the square root of 0.065 times 1.8 times 10 to the minus 4. And then we do the number crunching, 0.065 times 1.8 times 10 to the minus 4. And according to my calculation, this works out to be equal to 1. No, I have to run this off the 2 sig fig. So this will be 1.2 times 10 to the minus 5. What will be the next step after this?
Sure.
So you're talking about the percent dissociation. Okay, where am I going to fit this? You know what? Let me just erase the top part here so I can just continue that part of the calculation. So the percent dissociation or ionization would be equal to 1.2 times 10 to the minus 5 m divided by the initial concentration, which is 0.065 m times 100%. So let's see what that gives. 1.2 times 10 to the minus 5 divided by 0.065 times 100. And according to my calculations, and again, please check to make sure I'm doing the right thing, but I got 0.018%, which is obviously less than 5%, which means that assumption is valid. All right? So therefore, we can go with this to represent the concentration of hydronium, right? Or H plus. So based on that, we can calculate the pH.
The answer I'm getting correct.
Oh, my bad. Okay.
I put 1.2 times 10 to the negative 5 before I do the square root. 1.8 times.
Oh, so I forgot to do the square root. Thank you. Let me see. Let me do it myself again. Okay. Oh, right, I did forget to do the square root. Okay, so the answer I got here, or the correct answer here is 3.4, right? Times 10 to the minus 3. Thank you, Miss Morris, for that. Okay, so the x value here will be equal to 3.4 times 10 to the minus 3, all right? So that means we have to change this as well up here. So this would be 3.4 times 10 to the minus 3 m. So let's see what that gives. 3.4 times 10 to the minus 3 divided by 0.065 times 100. Okay, so we got a percentage which is greater than 5%. We got 5.2%. Greater than 5%. Which means that the assumption is not valid. So what does that mean? That means that life has become more difficult. What that means is that we have to go back to this equation here. We have to go back to x squared divided by 0.065 minus x equals to 1.8 times 10 to the minus 4. So just erase the rest of this crap. So, some algebraic maneuvers we have to make. That will be equal to 1.8 times 10 to the minus 4 times 0.065 minus x. And then we do the distribution, let me see here, 1.8 times 10 to the minus 4 times 0.065. So according to my calculation, this part here gives 1.2 times 10 to the minus 5 minus 1.8 times 10 to the minus 4, and then x. And then we bring everything over to one side, and you're gonna end up with x squared plus 1.8 times 10 to the minus 4x minus 1.2 times 10 to the minus 5, and that will be equal to 0. So this will be, so A is going to be equal to 1, B is going to be equal to 1.8 times 10 to the minus 4, and C is going to be equal to minus 1.2 times 10 to the minus 5. So what I'm going to do is go to my trusty quadratic calculator online. Okay, so the A value, now unfortunately for me, I have to include, I can't write it in scientific notation within, at least I don't know how to, maybe there's a way. But A is equal to 1, right? Now B is equal to what? 1.8 times 10 to the minus 4. So that is the same thing as 0.000 and then 1.8. Right? And then in the case of C, that would be minus 1.2 times 10 to the minus 5, so that would be 0.00012. Okay, and then I hit calculate, and let me see what the answers are. I got 2 answers. Oh, wait a minute. Something is wrong.
I think C has to be negative.
Huh?
C has to be negative, I think.
Thank you. Miss Morris is on the ball today. Okay. Oh, negative. Where is it? Come on. All right. Why is it not working for me here? Okay. For some reason, the negative side is not showing up when I press the button. Oh, let me try this. Okay. All right. So we got 2 values. Of course, the only one that will be valued is the one that is positive. So that means that x, x is equal to, okay, let me see what we have here. 0.0037, so 1, 2, 3. I'm just going to run it off to 2 sig figs. 3.3, I'm sorry, 3.4 times 10 to the minus 3. All right? So that's what x will be equal to. All right? So x will be equal to that, which means that that is also the concentration of, of the hydronium ion. So I'm just going to put this is equal to the concentration of H plus. So therefore, the pH of the solution is going to be equal to minus log of 3.4 times 10 to the minus 3. So let's see what that gives. 3.4 times 10 to the minus 3. And then I do the log minus, okay. So according to my calculation, this works out to be equal to 2.47. And that's how you do that. All right. So as you can see, it's a bit involved for weak acids. Strong acids, very easy to calculate the pH of, but for weak acids, you have to go through all these steps, especially if the percent dissociation is greater than 5%. If it's less than 5%, then things are a bit easier. But if the percent dissociation is greater than 5%, then as you can see, you have to go the quadratic route. All right? Okay, any questions about it? Any questions? Okay, can I, or may I, clear this? Okay, let me see here. So that was question 8. Okay. All right, question 9 is asking you to compare the pH of the following. Basically, what you need to do is calculate the pH of each of these solutions, and that's it. Which one is greater? Or maybe you don't need to. Hold on. Compare the pH of the following. What do they mean by compare? Because I can't tell which one is a weak acid, right? The nitrous acid is the weak acid because, of course, nitric acid is strong, right? So, and they have the same polarity. So basically, you can just say that I would just accept the answer being, okay, nitrous acid is the weak acid because nitric acid is strong. And also, they gave you the Ka value for the weak acid. I'm not sure they're requiring that you do any calculations. Okay, I would accept just an explanation like that for 10A. And for 10B, same thing, even though they're bases. Okay, now this one is asking for you to calculate the percent ionization of a 0.015 m acetic acid. So to do that, let me see. Okay, so again, I'm just going to use HA. Dissociating to form H plus and A minus. And initially, you're going to have 0.015, 0, change here will be minus x plus x plus x. At equilibrium, you're going to have 0.015 minus x, x and x. And then, assume, like before, x is much less than 0.015, which means that 0.015 minus x is approximately equal to 0.015, and then Ka would simplify to x squared over 0.015, and the Ka value is given as 1.8 times 10 to the minus 5, which means that x is equal to square root of 0.015 times 1.8 times 10 to the minus 5. And I promise you, I won't forget to do the square root this time. 0.015, 0.015. times 1.8 times 10 to the minus 5. Then I do the square root. And when I did that, please correct me if I'm wrong, I got 265. So I got 5.2 times 10 to the minus 4. Right? And that would be equal to the concentration of H plus. So the percent dissociation, which is what the question is asking for, is equal to 5.2 times 10 to the minus 4 m divided by 0.015 m times 100%. So let's see what that gives. 5.2 times 10 to the minus 4 divided by 0.015 times 100. So according to my calculation, this is equal to 3.5%, which is less than 5%. So therefore, the approximation we made is a valid one. All right. So that's all the question is asking for. It's asking for the percent dissociation. All right. Okay. Any questions about this? Any question? Any question? Okay. So if you understand that, then you should be able to do the B part. I'm going to leave you to do the B part. It's a base, ammonia, but it's the same idea. They gave it a KB for the ammonia. And let me see what's next. Okay, so this is asking for you to calculate the pH of the following solutions. Let me see, 11A. You should be able to do 11A, same idea as before. I stable, and then you do the approximation and so on. So I'm going to leave you to do 11A, 11B, 11C, D, and then number 12 you should be able to do. And guess what? Number 14 is a repeat of, I think, the first question. So we did today. So you can ignore number 14. I guess I was half sober when I was putting this together. Let me see, number 15. Okay, number 15 is a bit complex, but I'm going to leave it for you to do as well. So try that one. And, you know, if you have any problems, I may even discuss it in class next time around. And then number 16 is a doozy. But I'm going to leave it for you to try as well. If you have any problems with these, let me know, and then we can work on them next lab. Let me see here. Number 17 is a bit easier for A and B, and for C. Oh, okay. So yeah, try the others. Hold on. Let me clear this. Okay, so we did that already. Okay, let me talk about weak bases, right? If you understood what we said about weak acids, same principle applies to weak bases, all right? So ammonia is a good example of a weak base, right? It undergoes partial dissociation, and therefore, again, is an equilibrium system that's set up, and therefore we can write down a mathematical equilibrium expression for the dissociation of ammonium hydroxide, right? So this is the equation right here. The equilibrium constant is equal to the concentration of the ammonium ion times the concentration of the hydroxide ion divided by the concentration of ammonia, right? And this equilibrium constant has a special name. We call it the base ionization constant or the base dissociation constant, all right? So it's symbolized by Kb, right? Kb is equal to the base dissociation constant. All right. And again, the Kb can be used as a proxy for the strength of a base. Basically, the greater the Kb value, the stronger would be that particular base. So you can, again, compare the strengths of two bases by comparing their respective Kb values. The one with the higher Kb value will be the base that is stronger. All right. Now, basically, to solve problems involving weak bases, like the ones that we did for weak acids, pretty much you do the same thing, right? You set up your ICE table, based on the equation for the dissociation of the base. You find out what X is, but this time the difference is that X would be the concentration of the hydroxide ion. All right? In the previous examples, X would be the concentration of the H plus ion, right? So in these cases where you're solving problems involving bases to determine the pH of a weak base, once you get X, that would be the concentration of the OH minus. And if the question is asking for the pH, by now you all should know how to do it, right? You find the minus log of the OH minus, and then you subtract that from 14, and that will give you the pH of that particular solution, all right? And I think some of the assignment questions involve that kind of situation, all right? These are some bases, weak bases, and their corresponding KB values. And again, the table I showed you earlier has some weak bases on it, but the list is not as long as in the case of weak acids. Let me find it. Okay, dissociation constant. So up top, these are the acids, right? And these are the bases and their dissociation constant. Again, you'll have access to this, so you can refer to this table when you're solving problems involving, for example, determining the pH of a base, all right? So that's basically it as far as bases are concerned and their KB values. And here's where we're gonna see a relationship between the KB for a weak base and the Ka for the conjugate acid, right? Because remember, if you have a base, to get from the base to the conjugate acid, you add H plus, right? So the conjugate acid is an acid, and it's a weak acid, usually, and if it's a weak acid, it has a Ka value, right? And there's a relationship between the Ka value for the weak acid and the Kb value for the conjugate base, right? Now, we call that combination between of the weak acid and the conjugate base, or vice versa. We call that a conjugate acid-base pair, right? Now, this equation here shows you the dissociation of a weak acid, right? And the Ka value for that you can determine in terms of the expression. This here is the equation which shows you what happens when the conjugate acid is hydrolyzed by water to form a basic solution, right? And of course, there's a Kb expression for that equation, right? So if you add these two equations here, right, what will happen? What happens when you add two equations? Common items on both sides will cancel out. So what are the common items on both sides in this particular equation? The A minus and the HA. And what are you left with? H2O to give H plus and OH minus, right? And that equation should look familiar to you. What's that equation? What we call this? We call this the auto-ionization of water, right? And remember, there is an equilibrium constant for that as well. That is Kw. So my question to you is, what's the relationship between Ka, Kb, and Kw based on what you see here? And it's something that we learned in the previous chapter in terms of equilibrium. When you add two equations to each other to get the third equation, what do you do with the Ka values or the equilibrium constants to get the equilibrium constant for the final equation? What do we do? If you add two equations, right, each equation has their respective equilibrium constant, right? You add two equations to get the third equation, right? How do you get the equilibrium constant for the new equation? Exactly, you multiply them. So basically the Kw value is going to be equal to Ka times Kb, right? So the way you interpret this equation is that the Ka for a particular weak acid multiplied by the Kb for the conjugate base of that acid is equal to Kw, which is equal to 1.00 times 10 to the minus 14, all right? So basically, if you know the Ka, you can easily calculate Kb and vice versa for any particular acid, all right? And basically what that tells you, so that's where you get Ka, and if you want to find Kb, this is where you get Kb, right? So basically what that tells you is that there's an inverse relationship between Ka and Kb. The higher the Ka value for the weak acid, the lower be the Kb value for the conjugate base and vice versa. And going back to this table right here, you see that relationship. In each of these cases, if you multiply the Kb value by the Ka value, it's going to be equal to 1.0 times 10 to the minus 14. For example, in the case of the first one, 5.6 times 10 to the minus 4, if you multiply that by 1.8 times 10 to the minus 11, you're going to get I have here 1.008, but if you round out to two sig figs, 1.0 times 10 to the minus 14. And that's true for every one of these cases, right? The Ka of the weak acid multiplied by the Kb of the conjugate base will always be equal to 1.0 times 10 to the minus 14 at 25 degrees. As I said before, that's the temperature that is usually the value at which these values are quoted. So basically, what this tells you, because of the inverse relationship between the two, what that tells you is that the stronger the acid, the weaker the conjugate base, and vice versa, right? So if you take the extreme case of, let's say, hydrochloric acid, write this down here, HCl, right? We all know this is a strong acid, right? But the chloride ion, which is the conjugate base, is very, very weak. In other words, if this is infinitely strong, which it is, right? That means that the chloride ion is a very weak base. It will not react with water. It just sits there in water, does not react with water to make a basic solution, right? On the other hand, if you have a weak acid like acetic acid, I'm just going to use HA to represent acetic acid. So let's say this is weak, right? Then the A minus, which is the conjugate base, will be relatively strong. Now, these are relative relationships. In other words, if you look at the Ka for this and the Kb for this, the Kb for this will be higher than the Ka for that, right? However, the conjugate base of acetic acid, which is the acetate ion, is actually a relatively weak base, especially compared to the stronger bases like sodium hydroxide and so on. In fact, let me use sodium hydroxide. Or more specifically, let me use the hydroxide ion. The hydroxide ion, strong base, right? The conjugate acid of that base would be water. Water is very, very weak in terms of its acidity, all right? So I'm just trying to point out that there's that inverse relationship between an acid strength and the strength of its conjugate base, or vice versa. All right, what time is it? I think I'm gonna start. Oh, let me just point to this and then we'll call today. So this is basically another list of acids. Let me see what's happening here. I think what they have done is arrange them in order of increasing strength going from bottom to top for weak acids. So sulfuric acid. We all know sulfuric acid is a very strong acid. So therefore its Ka value is very large. And then when it comes to the conjugate base of that, it's very small. But if you come down to something like hydrogen phosphate ion, this is the Ka value, this is the Kb value. As you can see, the Kb value is large compared to the Ka value, and that's because this acid or this particular ion is a weak acid, which means that its corresponding conjugate base, relatively speaking, will be strong. Okay, I'm going to stop here for today, and we're going to continue this discussion. I thought we'd be able to finish this chapter today, but unfortunately, that's not the case. So we're going to finish this chapter next class. And again, if you have any problems with any of the assignment questions, you can we can discuss that as well next class. All right. Mhm. Mhm.
But you circled the equal sign for that. I was
No,
wondering.
no, because the equal sign wasn't there to begin with. Because I thought, when I first saw this, I thought you were saying 10 times this, because there's no, oops, there's no equal sign that was there,
No,
so.
that was like the number crunching, that.
Yeah, I understand now, but what I'm saying is, when you're setting up your calculation, I think you made the same mistake here as well. When you're setting up your calculation, make sure you put the equal sign there, because the equal sign was not there when I was grading it. You see what I'm saying? It wasn't there to begin with, that's why I circled it. I remember specifically that particular,
Oh, so you wrote it.
yeah, exactly, I put the equal sign in, because it wasn't there. Because at first, when I read it, I was initially kind of confused. I was like, you know, I thought you were saying that all of that was multiplied, and then I took a second look at it and I realized the reason why I was confused, because the equal sign was not there. Yeah. All right. Oh, lordy, I need a vacation. What's up?
Just in case the online submission is illegible.
Oh, okay. Okay, what am I doing? Okay, for those of you out there in Zoom, I'll be signing off right now.